give you information. Second thing that you can get out is that when you change the energy, right? So when you change this energy from here, you could actually change the pattern itself as you change the energy. For example, if you reduce the impact energy, right, of this electron beam, when you lower the beam energy, what happens is that the lead pattern actually expands. The number of spots you see becomes smaller and smaller. If you increase the beam energy, you see the grid, more of this grid as you shrink down. Okay, so that's a common thing that you see with lead pattern. We'll explain why that is so as you change the beam energy. Okay, so let's talk a little bit about this diffraction from a surface net, so grid, if you like, surface grid. So we are mainly dealing with elastic scattering with the low energy electron. So first thing is elastic scattering. So 100 electron volt electron beam going in. We are looking at 100 volt electron beam coming out. We are not sensitive enough to look at inelastic scattering. Okay, so that's first thing. So if you do that, you are treating the electron as de Broglie waves. Okay, so that means that you can convert the energy of the electron to wavelength, right? So you have a control of the wavelength of your wave that you send into your sample, right? So this is the voltage that you apply can change the wavelength of your sample, of the incoming wave. So it's the same thing. So in diffraction we talk about PLD, path length difference, between the original wave and the wave that scattered off, refract the wave, and look for the multiple of the wavelength. So when the path length difference, which is given by A, which is the distance between two scattering center, two scattering point, diffracting point, is multiplied by these two signs, the difference of the signs, of multiple wavelength, then you have a diffraction spot. Okay, so that's the whole point about this. And phi here is measured with respect to the surface normal. So usually you think of this. So here I have my sample. This is my normal vector, right? Usually written by this. And phi is with respect, this is phi angle like this. So that's my notation when we're talking about this phi angle that I have. Not because that could be confusion, because you could measure from the horizon, from the surface, but usually people measure from the surface normal. Is the reference point. So phi is measured with respect to the surface normal. So as a simple example first, let's take a look at this. So you start out with phi, the incident angle is 0, meaning that your direct beam, right? Remember phi is from the my surface normal like this, right? Phi is measured with respect to the surface normal. So if phi incident is 0, that means it's incident directly normal to the surface. Your electron is coming directly normal to the substrate. Normal incident. Then what happened? Then your diffraction relations, sign of incident drop out. This becomes 0, right? This term becomes 0. And so what you got is something rather simple. You have sine phi refracted is just equal to n lambda divided by A. A is the diffraction point spacing, in the diffraction point spacing. And if you convert what this lambda is, right? Lambda is related to by the de Broglie wavelength, and you can show that lambda is equal to just 1.5 divided by voltage, the bias voltage, which is the kinetic energy, corresponding to kinetic energy of incoming electrons, all taken to the square root. And A here is in nanometers, so unit, right? And then what you got is that the largest angle that you can have diffraction, right? What is the largest angle? The largest angle I can have is 90 degrees, right? Because at this point, I cannot go into the surface. So this is the limit that I would have diffraction spot from there, emitting from this way. So you put in phi reflected equal 90 degrees, you can work out this voltage correspond to really 1.5 n squared divided by this interlattice distance, right? Distance. So d here is the spacing between interpoint spacing between h and k. H and k are the basis vector that you have. Okay. So if you take n equal 1, in other words, if you just have one multiple of your wavelength, then you work out the voltage, what the voltage should be. In other words, if you want just one single set of the diffraction spot, right? What is the voltage you need, right? So what you can do is that if you know the B spacing, B1, B2, you can work out what the B's you want. You can substitute into this formula, and then you can find out what voltage you require to expand your diffraction path to just see one unit cell like this. Okay, to expand to the outer edge, if you like, of this diffraction path. So H and K are the reflect. In other words, so here will be 1, 0 or 1, 1 or 0, 1. The spot. Which spot that you want to see. So here, if I go back, this is my 0, 0 spot. This is my 1, 0 spot, right? If I want this, if I only want to see from here to here, right? I don't want to see all this surrounding unit cell. What is the voltage I need? I need to lower my voltage so that this spot move as far to the edge as I can, right? And the whole thing is got expanded as far as I can, because this is my reflect. And if we go to as far as the edge I can, in other words, I'm trying to move my diffraction spot, original here, all the way out to the edge of my torso screen, which is as close to 90 degrees as possible, right? Then I would get just one set of spot, and that voltage corresponds to this. There's my voltage. Okay, so that's what I meant by using this formula to figure out what is the voltage required in order to see just one unit cell, one with unit cell in residual space. Okay, so as we go up in voltage, the diffraction pattern, you see more and more diffraction pattern, because now you are accepting more and more this n. You have the n goes up because now you have n equal 2, n equal 3, n equal 4. Multiple, you really get, if you increase the voltage, more and more spots starting to come in. Instead of 1, 0, you would have 2, 0, 3, 0. As you increase, all the spots starting to move into your field of view that you can see. Okay, so that's basically it. Here I'm trying to illustrate with this plot from Summerjai's book, actually, not very well. Apologize for the quality of this. You can sort of see what I'm trying to do. You have these three, right? This is kind of like one pattern. This is a single pattern, and you increase the energy, you have this thing, more of this pattern shrinking in, and you see more and more diffraction spot. And this one, so when I show you this, you know that I'm increasing my energy, because this is lower energy than this, and this is lower energy than this, because I can see more and more spot as we go through. Okay, so just to close up, although we can see this arrangement, the key points that you can see lateral arrangement of these spot diffractions. While some spots are weaker than others, the strong spot are usually the substrate spot. The weak spot are overlay spot. Right? You can see this pattern, but we cannot tell really what they are, because remember,